Welcome students. Now in this video we are going to see about the energy considerations in the metal cutting operation. So see here, we already seen that the energy in the metal cutting operation, which is given as the energy, this is also, we can say that this is the power or the work done in the metal cutting operation, which is equal to the cutting force into the cutting velocity. And of course we are not taking into account the feed power, which is very negligible. So the energy we can have, it is Fc into Vc, cutting force into cutting velocity. But see, this total energy or total work done in this metal cutting operation is nothing but it is the summation of the energy or work done against the shear or shearing, that is work done in shear, plus the work done against the frictional force when the chip is moving along the rake face of the tool. Okay, so how can we write the work done in shear? That is shear force into the shear velocity plus work done against the friction or in the friction, that is frictional force into flow velocity, which is equal to Fc into Vc, isn't it? Now if we want to write what is the work done in shear, the work done in the shear, work done in the shear or shearing is how much? That is total work done Fc into Vc minus F into Vf, isn't it? Now see, if I take this Fc into Vc as a common from this, what we are left with 1 minus F divided by Fc Vc into Vf, isn't it? And we know that what is Vf divided by Vc? That is Fc into Vc into bracket 1 minus Vf divided by Vc is nothing but our cutting ratio R, that is R times F divided by Fc. Okay, so if I take some example on this, suppose in an orthogonal turning operation or cutting operation, if I say that the rake angle is 0, in orthogonal cutting operation rake angle is 0, then prove that the work done in the shearing is equal to the Fc into Vc bracket 1 minus mu r. What I am saying that, prove that in orthogonal turning operation with the 0 rake angle, prove that this work done in shear is equal to Fc into Vc into bracket 1 minus mu r. So see, we already are having this work done in shear, so just extension we have to made here, that is what is the relation between F divided by Fc when the rake angle is 0. Okay, now we already learned about this merchant force circle diagram, isn't it? So let us have the relationship between the frictional force and the cutting force. What is the relation? So no need to by heart the formula, as I told you, just go on simply having this merchant circle here, isn't it? So this is the rake face. Okay, Fc, Ft, Fsn, Fs, friction force normal to the friction force. This total angle phi plus beta minus alpha, this angle beta minus alpha, and this angle beta. Okay, so we want the relation between this F and FC. So here is F and here is FC. So what can we write? Say, what is it? Say this sine beta is equal to F divided by R. Sine beta is equal to F divided by R, and you can write this as cos of beta minus alpha is equal to Fc divided by R. Fc divided by R. Isn't it? Now you get the relation, that is here I can write this R is equal to F divided by sine beta, and here I can write this R is equal to Fc divided by cos of beta minus alpha. Isn't it? So just equate these two, that is F divided by sine beta is equal to Fc divided by cos of beta minus alpha. Isn't it? So what we need here, F divided by Fc. So F divided by Fc, what is there? Sine of beta divided by cos of beta minus alpha. But here in the question what is given? Alpha is 0, that is rake angle is 0. So क्या आएगा यहाँ पे? F divided by Fc is equal to sine beta divided by cos beta is nothing but what? Tan of angle beta, and tan beta is nothing but what? Our coefficient of friction. So हो गया proof. F divided by Fc when rake angle is 0, this is mu. So we get whatever we want, that is this work done in shear, we got it as Fc into Vc into bracket 1 minus mu r. Isn't it? So same thing they have asked for the proof. Isn't it? So this is how we can able to calculate or show. So the thing is that we can have the three energies here. One is frictional energy, shear energy, and addition of this is nothing but the total energy, which is Fc into Vc, that is the cutting energy. So you can put or represent the any energy in terms of the fraction of total energy. Say if I ask you to what is the fraction of friction energy in this total work done. So how to calculate that? The fraction of, say if I ask you the fraction of this frictional energy or frictional work in the cutting, then how to calculate this? So what is the frictional energy? Frictional force into chief velocity divided by what is total work done is actually Fc into Vc. Isn't it? And we know that Vf divided by Vc is nothing but what? This is R. Isn't it? We know that R is equal to T1 by T2 is equal to L2 by L1 is equal to Vf divided by Vc is equal to sine phi divided by cos of phi minus alpha. Isn't it? So we know that. So we can also write this. This is R into F divided by Fc. Isn't it? So this is the fraction of frictional energy in the total work done. If I ask to the fraction of what is shear energy, so what we can write? This Fs into Vs divided by Fc into Vc into 100. Of course you will get in percentage. Okay, that is the contribution of frictional energy, contribution of the shear energy in the total work done. Isn't it? This is how again we can able to calculate. Now after seeing these energy considerations, now what we are going to see is that the specific cutting energy, this is also known as the specific cutting pressure or specific cutting force. So what is the definition of the specific cutting force? Okay, it is nothing but the work done in unit time divided by the material removal per unit time. Okay, so this is actually given as the ratio of the specific cutting energy. Please remember it is represented by UC. Okay, U is the specific energy and it is for cutting, so that is why it is UC, which is equal to what? The work done divided by material removal rate. So what is material removal rate actually? The material removal rate. So now it is representing with the Q. So how it is calculated? So it is nothing but the area of the chip into cutting speed. Okay, the area of the chip to be cut. Please remember, area of the chip जो कटने वाली है chip उसका area into VC. So what is area of the chip to be cut? That is B1 into T1, isn't it? And in cutting operation, this B remains constant. Either you can write B1 or B, same only, into VC. So what is MRR? B1 into T1 into VC. The chip is going to be cut, which is in the material having the undeformed chip thickness T1 and width of the chip is B. Then the MRR, it will be in millimeter cube per minute, isn't it? Mm cube per minute. This is our value of Q. And what is work done? It is total work done or cutting में जो वर्क हुआ है, that is FC into VC divided by what? B into T1 into VC. Now this is the work done. Of course it is Newton meter per this is what? This is the volume, isn't it? So it is the volume or material removal rate you are getting here. So directly if I write in terms of, say, this is watt or in joule, and this, what is this? Mm cube, isn't it? So it is generally given in the unit of joule per mm cube, or if VC or VC get cancels, so what you left with? It is FC divided by B into T1, which is nothing but Newton per mm square. Newton per mm square. So that is why this is also known as the specific cutting pressure or force also. Please remember. So this is the specific cutting energy. In same fashion, we can able to write. Now see, as we define the specific cutting energy, we can also able to define the specific say shear energy. Specific shear energy. How to define? That is the work done in shear. Work done in shear divided by MRR, isn't it? MRR. So work done in shear is Fs into Vs divided by BT1 VC. So this is also in, you can get in joule per mm cube or Newton per mm square. Okay. Also we can define the specific friction energy. Specific friction energy. Friction energy. How will you get? That is work done in friction. Work done in friction divided by MRR. So also you can get the frictional force into flow velocity divided by BT1 VC. Here see what is Vf divided by Vc is nothing but R. So F into R divided by B into T1. That is again nothing but your the specific friction energy in terms of joule per mm cube or Newton per mm square. So this is how we can have the relationship between these energies: cutting energy, shear energy and frictional energy. Okay, now see, very important formula that you have to remember always in terms with the MRRQ and the cutting energy, specific cutting energy UC. So many times it is required in solving the numericals. What is UC? UC is equal to work done divided by MRRQ, isn't it? So please remember this power, work done is nothing but what? Power in the cutting operation. So power is equal to this Q into UC or UC into Q watts. Please remember, power in metal cutting operation is equal to what? Cutting. Power in cutting is equal to Q into, Q is what? Our material removal rate, MRR, into specific cutting energy. Isn't it? So you are getting this power in watts. So this formula you should remember. Okay.